Okay, finally we have come to look at the neural network section of Pytorch. So let's do that. And let's open Google Colab. And let's actually make a copy to the drive. Open a new tab. We can close this thing. Okay, let's quickly walk through this thing. The usual Matplotlib, we are not really using it. I think we will start using it in the next video, finally. And here we are defining the network, the neural network, okay? First, we are actually defining a class that contains the neural network, and then we are defining the neural network itself. So let's look at that. So import torch, just importing PyTorch, import torch.nn as nn. This is sort of the neural network defining module inside Torch. You could, if you want to call functions within it, you can go torch.nn.blah, blah, blah. Or you can just, if you do it like this, you can define nn dot whatever function, right? Similarly, we are importing a subset in some sense, a module within Torch as import torch.nn.functional as f. It is within Torch, so you could, in principle, every time when you want to run a function, you can go torch.nn.functional. Whatever function name. That's too long, therefore we just go f dot whatever function name. Okay, so these things just contract the length of the things that we have to say to call a function deep within a particular library. So we just saw a very brief overview of what classes are, and we are defining now a class called net, which is a neural network class with a particular architecture, right? So this is not a general neural network. We're defining a neural network with a particular architecture, but we're just defining the architecture, and then I suppose we will learn the parameters on the neural network through optimization, okay? And then we say class net within brackets nn.module. So we are kind of borrowing properties defined in this nn.module, right? So it's not, we're not defining a class completely from scratch. We're sort of borrowing or inheriting things from nn.module. So we'll look at that. Just like before, we initialize the class using these layers. So we say self always refers to an object, the current object that is being sort of manipulated or created that belongs to that class. And we say self.conv1, the first convolutional layer, equals nn.conv2d 1, 6, 3. So this just means that we are defining one image channel, 6 output channels, 3x3 square convolutional filter, I guess is what this means. And then we are defining another convolutional layer. So these with 6 inputs, 16 outputs, and again, a 3x3 convolutional filter. We are defining linear layers, fully connected linear layers, one with 16 times 6 times 6 inputs and 120 outputs, and another with 120 inputs and 84 outputs, another with 84 inputs and 10 outputs, okay? So, so these are standard commands in the NN module within the Torch library. And we're just instantiating or creating an instance of a fully connected layer, another fully connected layer, another fully connected layer, a convolutional layer, another convolutional layer, and so on. Here we're just defining them. We are not saying necessarily that the network has these things in that order. Here we're just sort of creating these layers, and then we can arrange them in whatever order that we need to do. Okay. Um, okay, so that's just defining some variables. Um, then what we do is define the forward pass through the network, right? So imagine you have the input layer, the next layer, next layer, next layer, so on, and then finally some output. What is that sequence of layers for this class of neural networks? So that's being defined here. Um, so X is the input to the neural network itself, okay? So self is the object that corresponds to a particular instance of the neural network. So that self is a neural network, and X is an input to the neural network. For instance, it could be an image. And here we basically are defining the sequence of function operations that take you from input to output. Okay, so it says X, that's the input, and then self.conv1 operates on that input. So first a convolutional neural network, specifically this convolutional, not neural network, convolutional layer. And then you get some outputs. And then those outputs are operated upon by a ReLU. And those outputs are operated by what's called maxpool 2D, which basically takes little regions of the neural net of the outputs and takes the maximum of those little regions and then provides that as the output. It's called the maxpool layer. Okay, so input, convolution, ReLU, maxpool, and then that becomes X, and then that gets operated upon by another convolutional layer, another ReLU, another maxpool. And then this command just essentially, if there are additional dimensions that, if it's sort of a multidimensional matrix and so on, it basically converts that or reshapes. This is a reshape operation. Reshapes that into basically a vector or something, reshapes into something simple. And then that vector with how many ever numbers, I believe, is then operated upon by a fully connected linear layer and the ReLU, another fully connected layer, another ReLU, another fully connected layer, basically these three layers with these three sort of numbers of inputs and outputs, and then out comes the output, okay? So this function is actually defining the sequence of function operations, the sequence of layers that correspond to the neural network, okay? This is just a function that is a helper function for this thing, which essentially, I think, figures out the number of elements in the array or something like that. Okay, you can check what that does exactly. Okay, so that's defining the class itself, right? So what we have defined is a neural network class with a very particular architecture with very particular numbers of neurons and so on. We've basically taken general neural network architectures defined in this nn.module module and created a particular neural network architecture. And then, so that's until here is the function. So until here is the class definition. All these things belong to the class definition because they're indented the same amount from this class sentence. Okay, so everything indented the same amount that is contiguous belongs to the same function or for loop or if set, whatever, right? So all these belongs to the class definition. And then here we are defining, so this is, I suppose, the end of class definition. Here we are saying defining a neural network class with a particular architecture. Here we are creating a particular instance i.e. object of the class net. Okay, so the variable naming, I would say, is a bit weird, but because I'm not a big fan of naming things small, net with small and then net with big N, but it looks like people like it. um, so this is a class, this is an object within a class. You could name this whatever you want. They just happen to name it a net with a small n, okay? So maybe I would have named it like net class or something, and then net object, who knows, yeah, okay? In which case I would have had to define this here as net class. But let me just leave this as such and run this thing. And it finished running, and then when you say print net, which is a particular object, it actually prints the sequence of layers that or that this particular network is composed of. We can actually try type net, net. So the net is actually a instance of this particular data type, I suppose. Okay. Okay. So what we've done is just define the net, a particular neural network. Here we can get some properties of the network. Let's actually see what properties that we can potentially extract from this network already. Let me do that here. You can say net dot, and then it's got all these properties. Okay, all these properties or attributes or functions that can operate on this particular instance of the net class. Okay, where did all these properties and attributes come from? Okay, so we did not define them. We just defined these particular attributes and a couple of more things. So if you go net dot, it's got con1, con2, fc1, fc2, fc3, and those are things that we defined. But if you just go net dot, it's got so many things. Eval, float, forward is something that we defined. Parameters, whatever, like lots of things. Share memory, share dict, training, 0_grad. Where do these things come from? They were inherited through this nn.module, which contains these other properties and things like that. Okay, so that's where they came from. We can just for fun say print net.conv1 or something. Let's see what that looks like. Okay, so that actually looks like con2d 1,6 kernel underscore size, blah, 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 all that. Let's see what happens if we do that. It doesn't like it. Okay, oops, forgot a parenthesis there. Okay, so that's basically telling us what the property of that particular layer is. Okay, and then we have this thing called net.parameters. Let's actually put net.parameters here and then run that thing again. Net.parameters, let me run that. Print net.parameters. It actually gives you the parameters that, well, it just says method for getting the parameters of this net. And then if we say open close brackets and run it, Well, anyway, so it doesn't say anything yet. Um, let's actually do this in the, it just says generator object, blah, blah, blah. Let's actually do this in the next one. Let me maybe run this thing and then show what I intended to show here. We are setting params equals list net dot parameters. And then we can say what the length of this thing is. Now, we can try to do, we can try to say print params. Okay, this is what I intended to do. We could have set this equal to params and then try to print that. I suppose when this was run, it didn't actually output the thing that it would output. But here we've set it equal to, or converted it into a list. So we could actually have done this thing, I suppose. So net.parameters just has this, well, object that will generate the list of parameters in the model, which is basically all the weights and biases. But it's stored in some manner. And when you say list of net.parameters, it actually creates a list that contains all the parameters. So let me actually run that. And you get this huge list of parameters, which I suppose are randomly assigned. Okay, so when you say print list of net of dot parameters, it prints out all the parameters that go into defining the model. I assume this might be like con1, maybe one of them is like a fully connected network, another would be con2, another would be another fully connected network, and so on and so forth. Okay. So that's, each one is a tensor. Each one of the thing is basically a tensor, and so on. Okay. So here what is being done is we are using this object to create the list of parameters and converting that into a list data type so that we can view it on the screen. Presumably, the print command doesn't quite directly work on the net.parameters method. Okay, we can create the length of params. We can extract specific attributes of this params array, and so on. Okay, and then print params is what we did, which is the same as doing print of list of net.parameters. And let me just comment it out. Okay. Okay, so here we are just trying out. So the net, this object, let me, just so that it's not horrible to look at, let me comment this out as well. So that we don't have all these parameters printed. It just became this small thing again, run this. Here, what we're trying to do is creating essentially 32 by 32 matrix, kind of example of an image, perhaps 32 by 32 image, and 1,1 would be, I suppose, mini batch size and something else, I guess. In any case, the index of the image itself. So we say input torch.random. We're just creating essentially a random image. And then we say net of input. So he takes in the image and then outputs how many of our numbers is the output of the neural network, I think it was 10. I think it eventually outputs 10 numbers because that's the output of the final fully connected layer. Okay, so out is going to be 10 elements large. Okay, print out. And here you go. So input is some 32 by 32 matrix. Output is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can see what happens if we change this to 2, runtime error. Okay, so the size of things need to match exactly the size that the neural network is expecting. This was fine. Okay, this was fine, and essentially it operates on each of these two, I guess, slices of the I guess in a four-dimensional matrix, and outputs the 10 numbers for each of those slices. Okay, so it just wants one here, but it can have how many ever. So suppose this is like having 10 images 32 by 32. Okay, 10 grayscale images 32 by 32. Okay, so and then the reason why this had to be one is because it's one here, which is a one input image channel. Okay, so this is assuming that there is one input image channel, and if you want three input channels, let's say for RGB, convert that to three, run it again, and you can then convert this to three. So let's try that. So to check our understanding, three input image channels, run this. Everything looks the same except we've gotten this changed to three. We can do that. One of them changed to three. And then now if we run this thing, we will get an error because probably because this one has only one input channel, whereas it's expecting three input channels. Okay, blah, blah, error. And we change this to three, and you're fine. Okay. So it takes 10 images, each with three input channels, each with 32 by 32 pixels, and then finally outputs for each of those 10 images, it outputs 10 numbers. Okay, so this need not be 10, this could be 15, whatever, how many ever, but for each input, for each of these sort of matrices of that size, it gives us 10 numbers as outputs. Okay. Okay. So this is the data input format. It's sort of analogous to how we had a four-dimensional array in MATLAB. This is very